Last time we talked about translations as our first type of transformation. Today we'll be talking about reflections, another type of transformation, and it should remind you a lot of a mirror. The key thing being the line of reflection. You can almost imagine that bird flip-flopping over that line. Reflections always make me think of this art project where you have like a blob of paint, that's the pre-image on a piece of paper, and then you fold the paper over this line and it produces an image of the paint because the paint transfers to the other side. So you'll hear me talking a lot about folding a piece of paper over a line when I talk about reflections, because here's what I'm picturing. There is our new image, and you can sort of see how it's equally spaced away from that line. And the little nosy part on the first one matches the nosy part on the second one because they sort of flip-flopped. So the first thing I want to focus on is getting the line drawn correctly. In each of these examples, it tells us which line is the line of reflection. So we just want to highlight on this first one, we're going to use the x-axis as sort of that folding line. On number 2, the y-axis. Number 3 is the line x equals -1. So if you go on the x-axis to -1, all the points that have -1 as an x value lie on this line. It's sometimes a little misleading because it's a vertical line even though it says x equals -1. Similarly, if y equals 1, we'd be looking at all those points that have a y value that's up at 1. Y equals 1 is a horizontal line. Number 5, y equals -x. If you want to think about that as an mx plus b, that would be -1x plus 0, which means we'll start at a y-intercept of 0 and go down 1 over 1, down 1 over 1, down 1 over 1. The line y equals -x is this perfectly slanted 45-degree angle line. And finally, y equals x, sort of the same thing. Y equals 1x plus 0. We start at 0 and we go up 1 over 1. You'll also notice that 1, 1, 2, 2, 3, 3, 4, 4, those are the points on the line. Anywhere where the y value equals the x value is included on that line. So here's the line we're talking about for number 6. So on the first one, if we were to fold this graph over the x-axis, where would triangle ABC wind up? It would wind up down here in quadrant 4 if we flipped it over. And let's just look at where each point would flip to. Point A was 2 above the line, so it would flip to 2 below the line. Point B was 4 above the line, so it would flip to 4 below the line. And C was just 1 above the line of reflection, so it would flip to 1 below the line of reflection. So A prime is going to wind up right here, B prime right here, and C prime right here. Does it look like that triangle got flipped upside down to you? If triangle ABC was happy, it would now be upside down happy. Let's do a reflection over the y-axis now. You can sort of picture that this rectangle is going to also wind up in quadrant 4 once it flips over. Let's be precise about it though. Let's do point A first maybe. So if A is 4 away from that line, it'll reflect 4 away from the line on the other side. So A prime should be right about there. Point B, same idea. B is 4 from the line, so it should wind up 4 from the line. Point B prime right there. Point C, only 2 from the line, so C prime only 2 from the line. And finally, point D, also 2 from the line of reflection, so point D prime 2 from the line of reflection. And it's important to note that on a reflection, even though that just looks like a congruent rectangle, the orientation is flipped, right? Because it got flipped over by a reflection. This one went from A to B to C to D. This one goes from A prime to B prime to C prime to D prime in the opposite orientation. The next one gets a little tricky because the line of reflection actually overlaps the shape we're trying to reflect. But if we keep the same principle, we know that A is 2 away from the line, right? So when it reflects, it'll be 2 away from the line. That puts A prime right here. You really have to focus on that line. B is 2 away from the line, so B prime should be 2 away from the line when it flips over. And this might feel a little weird. Point C is 1 away from the line. It's on the other side. So it is going to flip to the opposite side. C prime will wind up on the left side of the line. So that might feel a little strange because we reflected both ways across that line because of the position of the triangle. But can you see that triangle ABC and triangle A prime, B prime, C prime are still congruent to each other? They're just reversed. They're flipped over. And by the way, since the pre-image and the image are congruent, we can say that a reflection is, what's the word for pre-image and image being congruent? A reflection is an isometry. Number 4, we have another reflection that's going to go sort of up and down. We'll start with A. A is 1 above the line, so it will reflect 1 below the line. B is 2 below, so when it flips, it'll wind up 2 above. Same thing for C. And then D is 1 above, just like A, so it'll flip 1 below, just like A prime. And you can sort of picture that matching up if you fold it along the blue line. Number 5 gets a little trickier because the line of reflection is slanty, which means we're going to have to fold a little bit slanty. Since the line is coming down 1 over 1, when we reflect, we'll go up 1 over 1. So from A, it is 1 diagonal away from the line, so it will reflect 1 diagonal on the other side of the line. All the points will be counted that way. We're going to count up 1 over 1, up 1 over 1, and it took 2 of those diagonals to get to the line for B, so we'll do 1, 1 to find our B prime. What happens when a point is actually on the line? If it's 0 away from the line, can you imagine just folding that, and that point C and point D would both just wind up in the crack. So point C and point D don't move, so C prime is in just the same spot as C, and D prime in the same spot as D. Sometimes it helps me to turn my paper a little bit when I look at those slanty line reflections. It just helps me see it better. Last one, same idea. Since the line is going up 1 over 1, we are going to reflect going this way. A looks like it is 1 square diagonal from the line, so A prime would be another 1 square diagonal from the line. Let's try B. Looks like 1, 2, 3. So we'll go another 1, 2, 3, and that's where my B prime should be. And then C, a little tricky, it's like 1 diagonal and a half. So on the other side, we'll count that half plus a 1, 1 and a half on this side, 1 and a half on this side. C winds up right on that y-axis. Some interesting facts about reflections. A reflected image is congruent to the pre-image. A reflection is an isometry. The line of reflection is the, write this down and then I'll explain, perpendicular bisector. The line of reflection is the perpendicular bisector of AA prime, the segment. Let's look at some of our examples. If we draw in AA prime, the segment, maybe on number 3 here, what we see is that the line of reflection is perpendicular to that segment, and it splits it into congruent pieces, because that's how we designed it. A was 2 squares to the left, so we put A prime 2 squares to the right. If we look at one of these slanty ones, like number 5, AA prime, that segment is right here. And again, you see that the line of reflection is perpendicular to AA prime, and it cuts it in half. Perpendicular bisector. Here's a little picture of our parking lot. It says it's really cold today, and you always park somewhere along that back row of parking spots. And you go in the activities door, and then when you come back out, you come out the Sullivan door. And so this total distance here, we would want to keep you outside in the cold for as short a time as possible. So we're going to try to make that total distance the smallest. The question is, where do you park to make that happen? Should you park right in front of the activities door? Then you'd have a nice short walk here, but a longer walk there. Or should you park right outside the Sullivan door? Then your long walk would be in the morning and your shorter walk after school. But the question is the total distance shorter on this path or on this path? Or maybe we should strategize somewhere in the middle so that you kind of split the difference, that total path. Now, I think we can all agree that a poor decision would be parking like over here, because it wouldn't be very effective getting there and it would be super long way to get to the Sullivan door. So there's actually a strategy here that involves reflections. And I can choose either of those doors. I'm going to start with the activities door, and I'm going to pretend that I'm doing a reflection of that over that line back by Deacon Drive. So I would measure how far the activities door is from that line, and then I'm going to reflect it over into that field. And that whole perpendicular bisector thing is going to help me. I would use a ruler and make sure that this piece and this piece were the same length. So I'm going to call this spot out here activity door prime. And just one thing to think about, no matter where you park on here, the distance to walk to the activity door and the distance to walk to activity door prime would be the same. That's that perpendicular bisector theorem, right? And remember, we're trying to find the minimum distance. So if I parked here, I'd be looking at that total distance. If I parked here, I'd be looking at that total distance. I think it makes more sense drawing it like this because we know that the shortest distance between 2 points is a nice straight line. And so that strategy is going to tell us exactly where to park. We would want to park right here. Since this distance matches this distance, the combined total of going from this door to this door and then this door to this door would be minimized because it's the same distance as going from this star out to A prime. So that's a good strategy for staying out of the cold. I always have students that struggle on reflections like this. We're actually going to use a ruler to do it, but can you just make a prediction? Would you say that sort of the middle of this triangle would wind up closer to the number 1, 2, 3, 4, or 5? Once we reflect this triangle, where would that star sort of wind up? And I say that the correct answer is 4. Did you say 4? Because remember, when we reflect something, we're going to go perpendicular to the line, and we're going to come out the same distance away from the line on the other side. So I think the star would wind up closer to the 4. Now let's break out our rulers. Sometimes it's easiest to turn your paper. Again, like I said, it makes it easier for some people. So I'm going to start at point A, and I'm going to try to draw a perpendicular line through that line of reflection. And I think I'll just do that with points B and C as well. If I wanted to be really precise, I'd break out the protractor too, but to me that looks close enough to being 90-degree angles right there, yeah? So we've got the whole perpendicular thing. Now we have to work on bisector. So when I measure from the line to point A, I get about 2.4 centimeters. And so I'll want to also measure 2.4 centimeters on the other side of the line to find out where A prime goes. And I'm going to repeat that, just measuring those little distances from the line. Here I'm getting 0.4 centimeters, and here I'm getting 1.2 centimeters. So again, I will just measure that same distance on the other side of the line, using my ruler, trying to get as precise as I can. And I'd say that looks like a pretty good reflection, especially if you sort of turn your paper so that that reflection line is vertical. Maybe it'll help you see it better. And that is it for reflections.